Hello and welcome to section 8.1 in contemporary mathematics. In this section, I'm going to talk about gathering and organizing data. So let's head on over to the textbook here. And let's go through some of this information. So let's talk about what we're going to cover in this section. So after reading this section and watching this video, you should be able to distinguish among the different sampling techniques, organize data using an appropriate method, and create frequency distributions. So when you have polling organizations such as Gallup, what they're trying to establish is a general consensus or understanding of a population based on a sample. And so you'll often hear this with, especially during election seasons, talking about trying to predict which candidate is most likely to win. And so this is carried out by where a sample is collected from an entire population, and data that is what is collected. So for example, let me illuminate on this a little. The population of the United States is everyone within the United States. A sample within the population of the United States would maybe be like all of the individuals within Iredell County or Caldwell County or Los Angeles, California. So that would be a sample. Now those are particularly undiverse samples as far as the population is concerned, because the population of Iredell County is not going to be representative of the entire population of the United States. And the same thing with Los Angeles. You're going to have different, and it also depends on what you're trying to measure there. So let's look at this example. One of the famous failures of good sampling occurred first half of the 20th century. So the Literary Digest was among the most respected magazines in the early 20th century. And despite the name, the Digest was a weekly magazine. Started in 1916, they conducted a poll to try to predict the winner of each presidential election. Now, for the most part, their results were good. They correctly predicted the outcome of all 5 elections between 1916 and 1932. Now, in 1936, the incumbent president, President Franklin Roosevelt, faced Kansas Governor Alf Landon. And once again, the Digest ran their famous poll and results published the week before the election. And their conclusion was that Landon would win by a landslide of 57 to 43. But once the actual votes had been counted, Roosevelt ended up winning by 61% of the popular vote, which was 18 more than the predicted poll. So what went wrong? Well, in short, people who were chosen to receive the survey, which was more than 10 million people, they weren't a good representation of the population of voting adults. The sample was chosen using the Digest's own base of subscribers. Although 10 million was a huge amount, those pollsters were mailed a survey, and around a quarter of the surveys were returned. So this constitutes the sample that was used to make the Digest disastrously incorrect position. So there was some, and we'll talk about this later in this unit, but that's an introduction of something called bias into it. So there was another more complicated factor, was the low response rate. Only 25% of those who were surveyed actually responded, and that created what is known as a non-response bias. So the original type of bias was, I would probably classify that as what we call convenience selection. You just send out, and kind of like throwing spaghetti at the wall, right? You just send out as many and hope that it sticks. So that brings into this consideration of what does it mean to randomly select things? And so really, what is this idea of randomness, which is the important part of this next. When we talk about sampling a population and getting a sample, we want it to be as random as possible to ensure that we are minimizing bias. You cannot eliminate bias. There is always going to be some form of bias whenever you are talking about statistics. But how can we minimize it? Well, let's look at the different types of way we can gather data. So the first is what's called a simple random sample. And this is just basically you're drawing names out of a hat. And that's exactly what it says here. So you're just drawing names out of a hat. Another really good simple random sample, let's say that I wanted to pick a winner in this class who's going to get a free calculator or something, just something related to this course. When I can give everybody a number 1 through, let's say, 30, and just randomly draw a number, and the person with that number wins. And that's what it means to be simple random sample, is everybody has equal odds of receiving it, and it's pretty random. It's well kind of mixed up in the bunch. Now the next type is what's called systematic random sample. Now, systematic usually follows some sort of kind of rule, and so it is selected from an ordered list of the population, and so we decide what proportion of the population we want to sample, and we express that as a fraction with 1 in the numerator. So, 1 in 50, 1 in 10, 1 in 100, we want 1 in 1,000, and then we kind of every that many people, we will sample those. So let's say, for example, we wanted to sample 2% of the population. 2 out of 100 reduces to 1 out of 50. And so in this part, we can use a random generator to find a random number between 1 and 50. So let's use 31. In our example, our sample would be the units in the list at position 31, and then we would add 50 to that, and then 131, so forth and so on. Another good example of this is, let's say that we wanted to do 20%, a little bit higher rate. Then that would be 1 out of 5, because 1/5 results in 20%. So every 5 persons that walk in, or every 5th person, a better way to say that walks in, we would survey or we would count and make it. So that's what a systematic random sample is you kind of one in how many people, and then that if it's 1 in 50, then every 50th person you would select. If it's 1 in 5, then every 5th person you would select. The next type is what's called a stratified sample, and it is one is chosen. So is one chosen so that particular groups in a population are certain to be represented. So let's say you're studying the population of students in a large high school where grades run from 9th to 12th, then you want to choose a sample of 12 students. So if you use a simple or systematic, then you're going to, you might miss one grade completely. In a stratified sample, you would first divide the population into groups, also known as strata, and then take a random sample with each stratum, which is just the singular version of strata. So in the high school example, we would divide the population into grades, and then take a random sample of 3 students within each grade, and that would give us 12 students we need while ensuring coverage of each grade type. So for example, we can break them up into like letter grades of A, B, C, and D, and then we can pick, for example, 3 students from that. Another example we could do is, let's say I wanted to do a study on students taking math class. I'll use Math 110 because that's what this textbook is used for. And let's say I'm teaching 4 sections of Math 110. Then I can take 5 students from each section, and that would give me 20 students. And so I have a representative group from each of those sections that make up a sample. So that's a stratified sample in that case. And our last that is discussed in this book is a cluster sample. And this is a sample where clusters of units are chosen at random instead of individuals in a unit. So for example, if we need a sample of college students, we take a list of all the course selections being offered at the college, choose 3 of them at random, and then survey all of the students in those sections. So I basically did that very similar example, except instead of choosing specific students, that would be the stratified sample. If I sample everybody in those sections, that would be a cluster sample. Now, if there's only 4 sections, then you're not using a cluster sample. You're actually sampling the whole population. that would be everybody in it. So you got to kind of figure out what's a sample versus what's a population. Population is the entire possible representative group of what you're talking about. So if you're talking about Math 110 at, let's say, for example, Mitchell Community College, you're talking about every student who's enrolled in Math 110. That would be the population. So a sample of those would either be a specific section, if there's more than one section, or a random selected group of students. If there's only one section, you kind of have to break it down. So when people study, when they use statistics and they're going to do a statistical study, they have to figure out really what's their population and then build a sample from there. So let's look at, I'm not going to do all of these. Of course, you have, you can look at them in the book, but here we have random sampling. So each of the following situations, we want to identify whether it is a simple random sample or a stratified random sample or clustered or none of those at all. So postal inspector wants to check on the performance of a new mail carrier, so she chooses 4 streets at random. Among those, each household on the selected streets receive a survey. So she's going to select 4 of the carrier services, and then everyone within that group is going to get surveyed. So I would argue that that is a cluster. And so it is in fact clusters. That is a cluster random sample. Well, let's look at number 2. A hospital wants to survey past patients to see if they were satisfied with the care they received. Sorts the patients into groups based on the department and selects patients at random from each of these groups. So I accidentally gave away probably what the answer is because we've broken it into departments, and instead of surveying the entire department, we're just selecting specific patients, and so that would be a stratified random sample. Let's look at number 3 real quick. A quality control engineer at a factory that makes smartphones wants to figure out the proportion of devices that are faulty before they're shipped out. They're currently packed in boxes, each hold 20 devices, and wants to sample 100 devices. So he selects 5 crates at random and tests every phone in those 5 crates. So if you're selecting 5 of something and testing everything within that group, that's going to be a cluster. And so that's a cluster random sample. What about number 4? A newspaper reporter wants to write a story on the public's perception on a project that will widen a congested street. So she stands on the side of the street and questions and interviews and the first 5 people she sees there. So if you notice, there's no randomness to this. She's just kind of hoping that she can grab somebody and interview them. And so this actually has no randomness in it whatsoever. An executive at a streaming video service wants to know if her subscribers would support a second season of a new show. She gets a list of all the subscribers who have watched at least one episode and uses a random number generator to select a sample of 50 people from the list. So this is a simple random sample. It's kind of like names in a hat in selecting it. And then finally, I guess I did go through all of them. I'm reading these fairly quick. So an agent for a state's Department of Revenue is in charge of selecting 100 tax returns for audit. He has a list of all the returns eligible for audit, which is about 12,000 in all, sorted by the taxpayer's ID number. He asks the computer to give him a random number between 1 and 20. It gives him 15. The agent chooses 15, 135, 255, 375, and every 120th return after to be audited. So you can kind of see he's going every 120th. And so he started with 15 and then just is adding 120 every time. So that is that's what we called a systematic random sample. I lost the word systematic in my head. So anytime you're kind of, you did some randomness there, you picked, well, who do I start with first randomly, and then, I'm going to go 100 every 120. That would be systematic random. The randomness comes from where you started. So pretty good there. People in mathematics, this is George Gallup. Again, he's the founder of the Gallup Institute, which is a huge name in surveys and all of that stuff. So they're a very big organization today. So how do we organize data? Well, data is organized into two categories. So, and these are very important to know, categorical and quantitative. Oftentimes we can say, instead of categorical, we can say qualitative too. So I'll spell that here, qualitative. So you have qualitative data and you have quantitative data. So when I hear qualitative, I hear quality, and so it's a quality about something. And then when I hear quantitative data, I hear quantity, and that means that it is a quantity of something. Categorical data can also be something like yes or no. It could be true or false, something like that. That is categorical data. I always like to have students kind of think about this. The difference between, and well, let me talk about qualitative means that it's assigned a measurement. So we're measuring something, for example, height or weight. The book there gives caloric intake, so a person's calorie intake is quantitative data. But one thing to kind of remember, and it's kind of interesting, is that some things that look qualitative because they are a number aren't necessarily qualitative. Shoe size, at least US shoe size, is actually not a quantitative value. We are given a number. So for example, if you have a 10.5 size foot, yes, that is a number. That does not mean your foot is 10.5 inches long or something like that. It is just a categorical number assigned to your size of foot that someone within this, kind of size foot would fit it. And there, in fact, there's a US 10.5 and there's a UK 10.5 and there's different shoe measurements depending on where you go. And those are categorical, not quantitative. They're qualitative, actually. They're qualifying you into this particular shoe size. So shoe size is kind of interesting. I like to bring that up as an example of, something that is a number. You would think it's quantitative because it's a quantity, but it's in fact not. It's categorical. So let's look at doing something called a categorical frequency distribution. So let's talk about what's a frequency distribution. So a frequency distribution is you're basically counting how many of something are there. So let's look at this example to kind of show what happens. So a teacher records the responses of 28 students on the first question on a multiple choice quiz, and it's got possible choices A, B, C, D, and E. So here are your students. You've got 28 students, and they've answered A, B, C, D, or E. So to create a frequency distribution, what we would do, let me go get a different color here. All right. First, let's count. To create a frequency distribution, we want to count the number of A's that there were. So if we do that real fast, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got 13 A's. Then we would count how many B's. So I see 1, 2, 3, 4. So 4 B's. And then we would count the number of C's, D's, and E's. And so that's, you would continue that, and that's kind of how it looked. And I apparently missed one. So there was 14 A's and 4 B's, 6 C's, no D's, and 4 E's. And again, this was what they answered, not what they made, right? And so a frequency distribution would literally just list the response and how many times that responded. And that should, of course, add up to 28. So you can see that you can kind of, a benefit of a frequency table is just to be able to look and say, well, what did they answer the most? And it's clear that A was answered the most. It had the highest frequency. What did they answer the least? Well, it was D. Nobody answered letter choice D. And so you have that frequency. And so that is a frequency distribution table. Now for quantitative data, we can also do a frequency distribution. And so if we do the same thing here we've got how many siblings do you have? That's a quantitative amount. Although it's kind of interesting, you know, it is a quantitative amount, it's a quantity, but you have to be careful when you talk about like averages and stuff because you can't have like half a sibling. But anyway, so again, first thing you're going to do is count how many different responses you have. And I'm just going to jump down here. So if we look at this table, number of siblings, how many people had 0 siblings? I see 1, 2, 3, 4, 5, and that matches the frequency here. And then they've done a double table, so 0, 1, 2, 3, 4, 5. So somebody had 5 siblings. Oops. And there was only one person that had 5 siblings. So you read it going down this column. Let me get my pen out. So go down, the way to read this table is you go down this column, and then it jumps over here and goes down this column. So don't be confused by that 2 tables in one kind of deal, or this table is, you know, 4 columns. I don't know. This is written weird. But you can kind of see that who's most frequent. Well, the number of having 1 sibling is most frequent. 13 people have 1 sibling. What's the least frequent? Well, that would be 5 siblings. That's the least number of siblings. So another thing that you can have for quantitative data is something called a bin frequency distribution. And so when we talk about bins, we're talking about, because quantities can fall within ranges. So like if you're talking about height, you could be talking about people who fall within 5 to 6 foot, or 6 to 7 foot, or 4 to 5 feet. So you can have ranges of where something falls. GPA is another good example that can be put into bins. So like 2 to 2.24, and then 2.25 to 2.49, and then 2.5, so forth and so on. So they all have bin widths of 0.25. You may talk about heights, you know, in inches, and so maybe every 10 inches is a different bin. So let's look at that example. Now with this table, if you're reading this in the book, you have to be careful because this table actually is kind of long. It's kind of a big table, so you do have to scroll this way. One thing that the book talks about is you kind of want to keep your bins into about 7 or 8 bins is the number of bins that you want to have. And I'll highlight that right here. That's just a rule of thumb. That's not like you have to have 7 or 8 bins. It's just a good kind of starting place. So what we have to do first is we have to figure out what's going to be our bin size. All right, so we have to first find what our max number is. I can't really highlight well. So what's going to be the highest? And that's going to be 4.0. So a 4.0 GPA, highest GPA you can have on a 4.0 scale. And then we need the lowest GPA, which let's see, we have 1.2 is pretty low. Let's see, make sure I got this. Yep, 1.2. So 1.2 is our lowest GPA. So to find our bin size, what we're going to do is we're going to take our highest GPA, which was a 4, minus our lowest GPA, which was a 1.2, and let's divide it by 8. Let's have 8 bins. That's going to be our 8 bin sizes. So if I do 4 minus 1.2 and divide it by 8, that gives me 0.35. So what that tells me is my bin sizes are going to be 0.35 in length. So I'm going to start at a 1.0 GPA, and I'm going to go up to 1.35. Sorry, 1.34. I just want to stop right at the edge of that bin and then pick up at 1.35. And then I'm going to go up to the next one by adding 0.35. And I'm going to stop right before that, so that's going to be 1.69, and then so forth and so on. So let's look at that here in the show solutions. Let me get that scroll issue fixed. There we go. So let's look at that here in the solutions. So you can see that the minimum was 120 and the maximum was 4, so we have this bin size of 0.35. So we get these bin boundaries of, well, I guess they're starting at 1.2 because that was the lowest value. That makes sense. All right. So let's do that. So 1.2, 1.55. And so it goes, no, it starts at 1.0. I'm sorry. That's what I wanted to do, right? And then we go up to 1.33, and then from 1.34 to 1.66, and then 1.67, so forth and so on. So you can see we're increasing by that amount every time. They do change it to 0.33 since it's so close to 1/3, and so that's arbitrary. I'm not 100% sure why they really do that. Then it says because these are GPAs, they are natural breaks at 2.0 and 4 and 3.0, and that's important. And so they probably do that so that the math kind of adds up to get you to 3.0, and that's perfectly fine. They're kind of naturally making it jump up to the next 2.0, 3.0, 4.0, which that makes perfect sense. And so the frequency would be then for this bend distribution we would go back to the table and we would figure out how many GPAs fall between 1.0 and 1.33. Well, there's only one, that was 1.2. And we would continue to do that for all of these other GPAs. And kind of see where it falls and then how many are within each bin. And so what that allows us to quickly do is say, well, what's the highest, kind of bin of GPAs? What do most students come out with GPAs of? And that would be this range right here, which is a 2.67 to 2.99, which is that's a D GPA, or is that a C? That's a C GPA. And then, of course, all of our frequencies add up to the total number of students. So that's kind of what a bin frequency looks like. For quantitative values is you create these bins. Again, the bin values you're allowed to kind of mess with and change depending on what you want to do in order to get the bins to fit well. So that's all I have for this video. You've now watched this. Hopefully you've taken some handwritten notes. Make sure you read the section. I skipped over several of the examples, but go back, do the your turn problems, and make sure that you are understanding what I'm talking about and what's being talked about in this section. And then when you're done with that, head on over to the LMS and work on the online homework.